Okay, so the nature of programming. This is going to be pretty brief. I'm not going to get into too much detail about these, but I think you'll hopefully have a better understanding when we actually describe the compilation pipeline after we go through this. So machine language. Each instruction that we're going to have our computer perform is going to be encoded as a binary sequence of numbers. The language of these instructions is going to be known as machine language. Now, MIPS is a common machine language used in, say, architecture classes. It's going to be slightly less complicated, or perhaps more likely, or a lot less complicated today than what the instruction set of, say, an Intel processor may look like. But I'm going to go ahead and use MIPS simply for its simplicity. If we wrote, say, a high-level statement such as wage is equal to rate times hour, this would eventually get converted down into the following four MIPS language instructions, which would be provided to a processor that would understand these instructions. The first thing is go out to memory and grab the value and rate. Go out to memory, grab the value in hours. And we're going to store these in what's known as registers, which are like sitting pretty much right on the hardware that's going to perform this computation. So it's very near to it. Next, we're going to perform a multiplication of the values in those registers, and we'll have to write that value into another register. Look how atomic this is. It's go get the value, get the other value, make sure they're both stored, perform a computation, the multiplication on that. Okay, store that result in a register. Now go get the value stored in that register and go ahead and write it out to wherever the memory location for wage is going to be. So this is one high-level statement boiled down to four instructions to actually perform that computation. Now, writing in binary is no fun. If you could think about, early days, it would not be very desirable to think in terms of these cryptic kind of ones and zeros. You may have to in your architecture class if you go on through our curriculum. I know I did when I took it as an undergrad at Trinity University. We were thinking about things in binary and hex kind of a lot throughout that course. And it's a very interesting perspective because it is actually looking at what these high level statements actually are, how they're actually executed. And it's if you look here, it's again, very kind of stepwise, and there's a lot of processes or a lot of instructions rather to even implement kind of this trivial expression that we have. So to get around thinking in binary and having to write all of these ones and zeros out, assembly language came around. So assembly language has an assembly instruction for each machine language instruction. And we'll see here that an assembler essentially takes the assembly language and converts it into the ones and zeros, the machine language that we saw on the previous slide. So unlike machine language, assembly language is entered as mnemonics, so words that describe what they do. So that same instruction, wage is equal to rate times hour, can be written in a lot more readable and perhaps desirable fashion. So those load operations, LW would be the mnemonic for load words. That would be, again, going out, pulling that the value stored in, I guess, rate came first, we said, rate, and storing it into a specific register, doing the same for hours. Multiplication, this is a lot easier to understand kind of what's going on here. We're multiplying the results, multiplying the values, and it looks like register 2 and 3 together, storing that result in register 4. And then finally, we're going to take that result and write it back into wage. This is a lot kind of less cognitive overload to write things in this fashion. And again, in that computer architecture class, we not only wrote in ones and zeros, but we also spent a lot of time in assembly language. And you really can come to appreciate what high-level languages afford when you're forced to kind of think about how things are actually occurring on the processor level. So admittedly, it is hard to express ideas in machine language and assembly language. If you look at the kind of level of abstraction, if you will, that you have to focus on to do any sort of interesting computations, it does become it becomes a lot more, I guess, non-trivial to actually do. You have to think about, again, each step in the process and not just the process as a whole. It has to be composed into its part. So higher level language use more complete mnemonics and also more complex organizations of ideas. It I don't want to say it's as similar to natural language, but it's a lot more similar than, for us, I think, than thinking in ones or zeros um, in terms of implementing our ideas. So in C++, provided that wage has been declared, as well as rate and hours have been defined, we could simply write the following statement in our program: wage is equal to rate times hours. And what we'll see when we discuss the compilation pipeline is this simple statement is essentially taken into the compilation pipeline. It gets converted into assembly code, and then that assembly code gets gets converted into the machine level instructions that are required for the particular system that you are on to execute that command.